Welcome to the third lecture of Newtonian gravity. In the previous lecture, we discussed two equivalence principles by Galileo and Newton, and in this lecture, we will build up on them. So let's start by summarizing these two equivalence principles once again, and to highlight the key fact. So Galilean equivalence principle tells us that there is a equivalence between motion under inertial force and motion under uniform gravity. So key point is that the gravitational force should be uniform. It should not vary across the lab inside which you are performing the experiment. Also, it should remain constant over the entire duration of the experiment. And that gives rise to the fact that the freely falling reference frame under a uniform gravitational field can be thought of as the local inertia, where basically the Newton's law. Newton's equivalence principle states that gravitational mass is equal to inertial mass, mg equal to m. And for point objects moving or accelerating rather in a gravitational field, equation of motion is the following. So this side comes from basically the Newton's second law. Inertial mass times the acceleration is equal to the gravitational mass times the divergence of the gravitational potential. And this part basically comes from the Newton's law of gravity that we are discussing over the last two lectures. Also keep in mind that these statements are valid only for the Newtonian theory, that is, we work in a non-relativistic limit. All the velocities are much smaller than the speed of the light in vacuum, and also the gravitational forces are weak. It is weak compared to the binding energy of the object at the MC square. And these are summarized in this box here. We will get back to this limit as we proceed with some more lecture and critically take a look at this non-relativistic limit. But please keep in mind that these are the limit which sets the regime of validity of the Newton's theory. Now the question arises that can we perform a local experiment to distinguish the effect of gravity and make sure that this is not equivalent to inertial force or a pseudo force? And we say the telltale sign of the gravity is basically the tidal force. So that is what we are going to discuss. But before that, let's critically look at this equation of motion and try to generalize it or write down the corresponding equation for an extended object. So note that for the extended body, so accelerating in a gravitational field over a certain region, the acceleration of its center of mass is basically given by this. So again, this side comes from the Newton's second law, and this side comes from the Newton's law of gravity. So rho g is the gravitational mass density of this extended object, and you see that this integration over this x prime is basically over the whole volume of the body. Now, when can we get back our previous equation for the point particle? So there can be two things. Either you replace this rho g by the point particle mass density, that is m times some delta function, then it will give you this previous equation back, which we have written here. Or you can make an approximation such that the gravitational field remain approximately constant over the entire volume of the body. Then you can take this out of the integration, and then integral over rho g gives the total mass, gravitational mass mg. And then if we invoke this condition, that is the mg is equal to mr, then again both sides there will be cancellation and we get back this equation. But remember, typically the gravitational force varies across the body. So this thing is not a constant. We cannot take it outside of this integration. Only the special case is the spherical body, where we know the potential due to a spherical body is same as a point particle, the same mass located at its center. But except that, for any arbitrary body which is not a spherical object, typically it is so. So we cannot cancel. We cannot cancel straightforwardly the mi and mg unless otherwise we can take it outside. That is gravitational force has to be. So let's keep this in mind, and now we go forward to discuss the tidal force, which basically gives us the telltale effects of that. Now, as we say that gravitational force vary across extended object, we hardly deal with point particle, which is just a mathematical simplification. So keep that in mind. Let's construct a scenario through which we will arrive at the expression for the tidal force. So let's consider that there is a reference frame attached to the Earth and it is at rest, and then there is a rocket or spaceship moving in a stationary orbit. Remember, stationary orbits are the provide you a free falling reference. So, and then there is a coordinate system that is attached to the rocket, such that the origin of the coordinate system O coincides with the center of mass of this rocket, of the spaceship. And because this is moving in a stationary orbit, the center, which is denoted here O, the origin O basically, is freely falling under the Earth's uniform gravitational pull. Now consider a point P with respect to this origin O inside the spaceship, and which is at a distance x from this origin. With respect to the Earth reference frame, this is at the location which have a position vector capital X. And also consider that the radius of this orbit of the stationary orbit is r0. So capital M is the mass of the Earth, and small m is some mass of some object which you can put at this point. Now we know that there is a variation of Earth's gravitational field inside this rocket, and at point P, due to this variation of this gravitational field, there will be a tidal force, which we denoted by F. So the F here is comes from the variation of this gravitational field with respect to this origin O, and then we can rewrite in terms of the potential followed and which is evaluated. So see, there is a second derivative of this gravitational potential evaluated at x now, and this is you should try to derive this expression. We leave this as a homework problem for you to derive this expression. And we also introduce quantity which is denoted by this symbol. This is actually a tensor quantity, and we term this as a tidal force tensor. We will later see that this Ri0J0 is related to a component of the Riemann curvature tensor, which gives information of the curvature of the underlying space-time geometry when we will discuss differential geometry in the later part of the course, and that is why this curvature tensor are called the tidal tensors. And we will see that if we take a non-relativistic limits of the geodesic deviation equation, we will have this precise equation. So it's important that we know how these equations come, and please try to derive this equation. Now let's give us some bit more details about that, so that you will be able to derive this expression. So let's consider again the same scenario, and align the coordinate, the reference frame at Earth and at the rockets such that their z-axis coincide, and this orbit, as we say, its radius are not the surface of the Earth to the point O origin. And remember, this O is also coincide with the center of mass of the rocket. And this is a stationary orbit, so this O is at free fall. So let's consider a particle which is at the located at this point with respect to this origin O. So basically, it is located at this 0, 0, z, which is on somewhere on the z-axis inside the rock, shown in this cartoon. So now the gravitational acceleration for this particle due to the Earth gravitational pull is given by this, because with respect to O it is at z, but with respect to R it is R naught plus z. So, and we know that it is G times capital N by R naught plus z also. Now this origin itself is at free fall, so it has an acceleration due to the Earth gravitational pull, which is denoted by, right? This origin is the R naught distance. Now the relative acceleration of the particle with respect to this origin O inside attached, which is the origin of the coordinate system attached to this rocket, is the following. And if you simplify this, and assuming that R is very, very large than the Z, then approximately this will come. Remember here, this relative to this reference frame attached to the center of mass of the rocket is very important. We are always measuring the relative acceleration in a reference frame with origin when is freely falling, and that relative acceleration is giving rise to this tidal force. So here we have written down the tidal force on the particle relative to the O is given by this expression, and we see that it's a repulsive force. And repeat the same exercise for particle located at this point 0, y 0 relative to this O, and you can similarly calculate the expression for the tidal force for that, which is given here, and also do it for the when it is located at x, 0, and the corresponding expression for tidal force is here. So you can see from here there is a negative sign, and this is means that force is restoring towards the origin. So suppose there is a soap bubble inside this rocket whose center of mass coincide with the origin, that is, it coincides with the center of mass of the rocket. So due to this tidal force, it will be stretched along the z direction and will be squeezed along the other direction. So if we start with a spherical bubble, it will be deformed, and that is precisely the effect of tidal force. Again, to just to reiterate the fact that we are measuring the relative acceleration from the center of mass of the rocket to any other point inside the rocket, and that gives rise to this tidal force, which is basically the variation of the gravitational field across the rocket with respect to the center of mass. Okay. Now, if you collect all this expression and bring it into this form of the tidal force, which I have written down previously, let me go back to it. So in this form, so collect all these expressions, and you can then explicitly write down the various components for this tidal force tensor. So let me show you. So then in this particular example, so this tidal force tensor take this following form. So you can see the two, it's actually diagonal. So it's so it has two index. So both takes three values, x, y, z. So it's a 3x3 matrix, and see that only the diagonal components are non-vanishing. So first is the x component, which is 1, y component 1, and this is -2, up to the overall factor of gm by r naught cube c square, and c square is their dimensional reason. So one thing you should also check, given this expression for the tidal force, that the divergence of this tidal force vanishes when there is no matter density present. and that is equivalent to the Laplace equation in the vacuum. So this you can reformulate your gravitational force in terms of this tidal force in the Newtonian theory. So they contain the equivalent information. So to end, we all know about these various phenomena of tides, but there are various interesting astrophysical phenomena also relating to these tidal forces. For example, tidal locking of the moon. Also, these tidal disruption events. So what happens is that suppose there is a very big star and it imparts a very strong tidal force to a nearby small star, such that it gets squeezed and eventually broken down into space. And these tidal disruption events are very important astrophysical phenomena, and we encourage you to actually look into these events and see what are their importance. So we will end here, and thank you for listening.